Okay, so since I think I will not have that much time, I think I should start now, and we will see whether we've got time for a short break in the middle of the lecture today. So I will start just by reminding you of what I was doing yesterday at the end of the lecture. I was trying to write down an explicit formula for the omega GNs that you compute by topological recursion for an arbitrary local curve of this type. So these local curves, they are parameterized by an infinite number of parameters, which are this H and B, where the index I, I1, I2 range from 1 to capital N. And so KL go from 0 to infinity. So you've got an infinite number of parameterizing a curve. And you want to have an explicit expression for the omega Gn built by the topological recursion. What I told you yesterday is that this you can get it by writing it down as a sum over trivalent graph from the definition. And this sum over trivalent graph, I reorganized it by having parts of this trivalent graph which only know about the part in this omega 02 and omega 01 with BKL vanishing, which were these red clusters. And everything which had information about this B, I put it in these green edges, which end up in saying that the omega Gn, you can write them as sum over graphs, which are built in the following way. You've got this red cluster, which I will now replace by red vertices, each of which have a genus attached to it. So if I had a cluster which shows a graph of genus G, I replace it by a vertex of genus G. Each of these red cluster was carrying an index as well, which was telling me which I was using in order to do this recursion, so which was the I associated to each of the trivalent vertices. And now the only other output I was having, so I replace it by some red vertices of this type. And so I was just linking them by blue edges, which didn't carry any index. And now I had some leaves, which just correspond to, which was replaced by this, which actually I could write in white because it was the sum of the blue and the red contribution. So let's put I1 zeta 1, I2 zeta 2, I3 zeta 3. So omega Gn will be a sum over a graph of this type, to which I will associate a weight in a minute. Now the only thing I want to tell you is that such graphs are called stable graphs. And what I call a stable graph is a graph of this type. So you've got, for each vertex, for each vertex, you've got a genus which is associated. So you've got a map from the set of vertices of your graph, gamma, to n. You've got also an index I, which is carried by each of your vertices, and I belongs to set 1 to capital N, which is the different value I can have here. And I'm saying that these graphs are stable because if I consider a vertex, what I require is that 2 times the genus associated to this vertex minus 2 plus the valency of my vertex should be strictly positive. So in particular, if the genus is equal to 0, I need to have valency at least equal to 3. Yeah. Yeah. What do you mean no is here? Yeah. Yeah. So there is no blue. So you will have just stable graphs which are just one vertex. Indeed, that's exactly that. So what I call a stable graph is a graph which has this kind of restriction. So yeah. Yeah, so the genus of my graph gamma is equal to the first Betti number of this graph, so the number of loops, plus the sum over V in my over vertices of the G of V. Yeah. It's the valency of V. So basically, if you've got a vertex which has genus 0, it needs to have at least 3 legs going out. Now, actually, I've been just a bit short here. In order to get stable graph, what I've got to do is what I did in the first part of my lecture yesterday in order to introduce the H here. You remember that I said that introducing the H was just amounting to introduce some new type of vertices. So here I've got 2 types of leaves. One type which is corresponding to my, my outer variable, the n here. So I've got n leaves of this type, which are labeled by some I and zeta. And I've got another type of leaf, which was this cross leaves, which are associated to this part. And the red vertex, they just correspond to the omega gn that you would compute by topological recursion by switching off all the b's and all the h except for the first one, except for the h1. Now the result is that the omega gn of I1 theta 1 up to In theta n is equal to the sum over stable graph of genus G, where the genus of my graph is given by this formula, with n what I will call ordinary leaves. So what I call an ordinary leaf is a leaf of this type, which is white in this picture, which is labeled by the argument of my function omega gn. Yeah, it can be. Yeah, I did put them. Yeah, could have something like I4 theta 4. Right. Yeah. And now I will. So. Yeah, it counts for the valency. Yeah, it does. So the valency is the total valency. So if you want, you've got, in the following we will see it, but right now, you've got half edges coming from either internal edges or from leaves. And let's say you've got 3 types of half edges, just the ordinary leaf, this X, which will be called dilaton leaves, and this inner half edges. And they all count for the valency. It's the number of half edges incident to a vertex. That's the valency of a vertex. And now, what is the weight of such a graph? What you do is that you compute omega G of gamma, valency of gamma. So if you've got a vertex, V, you just look at the omega GNs that you would compute by topological recursion on the curve where you don't have either H or B. So it's the simplest case possible. The first one I did compute. So you make a product over vertices in gamma. You take the omega that you would compute for, I will call it KdV, where omega Gn KdV of C1 Cn is the result of topological recursion for the simplest curve omega 0, 1 of z is equal to 2z squared dz, and omega 0, 2 of z1, z2 is equal to dz1, dz2 divided by z1 minus z2 squared. So this is a very simple object, which we did compute first in the previous lectures. So to each vertex, you associate such omega g. Then, so here, remember, you've got vertices here. So you've got some internal arguments, C1, C2, C3, and so on, associated to each of these vertices. So to each vertex of Valenciennes, you've got a valency val of V. You've got V variable around it, which are either of this type or coming from these X leaves, or the last one can be coming from this original natural leaves, which are, in which case what I call capital Z is just the zeta, which is there. So here you've got a bunch of Z1 to Z valency of V. Now, this is the weight associated to each of your vertices. For each internal leg, the blue line here, for each internal edge, the blue line here, you remember it was just standing for this information. So it was just the generating series of this BKL, which I called omega 0, 2 regular of theta 1, I1, theta 2, I2. So you've got such a weight for each of them. Product for the edges inside of omega 0, 2 regular of I0 of E, C0 of E, I1 of E, C1 of E, where once again I0 and I1 correspond to the origin and end vertices, so the index I associated to the vertices adjacent to E. Because this is symmetric, so this seems to be depending on the orientation of my edge, but this omega 0 to regular is symmetric by definition, so it doesn't depend on this orientation. Now, for all the leaves, which are the ordinary ones, these ones, you've got a weight which come from the full omega 0, 2. So product from I ranging from 1 to n. So you've got n ordinary leaf, which go from a vertex V, E of, let's call it V1. So V1 is the vertex adjacent to the, Vi is the vertex adjacent to the ith ordinary leaf. And Zi is the corresponding Z. And here you've got now, should call it J. No, they're not to confuse notation. So yeah, I call it capital Z. So for the variable I will integrate, I call capital Z the zeta. It should be, should be a capital zeta if you want. But the second one will be the zeta I have. So it's Ij zeta J. So in my notation, capital Z, they stand for zeta I would integrate. So this is for the ordinary leaves. And you've got a last weight, which I didn't give you, which is the weight given by this X here, which are what I call dilatant leaves. And remember, they were just standing for the introduction of this H here. So it will just be a product for H being a dilatant leaf. So this is just this X cross here, which goes from a vertex with index G and I. And so you've got some variable here you will integrate, the H. The weight of such a leaf is given by just sum over K from 1 to infinity, H2K plus 1, capital ZH to the power 2K DZH. Now, I've got this which depend on a lot of capital Z's, and I just take the residue when all the Z's goes to 0. So I've got a function of a bunch of Z's, and I just take the residue of when all these Z's goes to 0. It doesn't depend on any ordering of the residues, actually. And if you check it, this gives you a symmetric formula here. And you can compute what the result of this equation is that it gives you a sum over stable graphs gamma of the same type, and you've got a weight W of gamma, where now I will have another decoration, which is the following one. Whenever I've got a half edge inside this graph, I associate to it what I would call a degree. So it's a positive integer. So this is a sum over a stable graph was half edges are decorated. And in the following sense, it means that I've got a degree which is a map from the set of half edges of gamma to the set of positive integers. So now the graph I have, I will just draw it a bit differently. I forget about this blue and red stuff, so I will write everything there. In this form, I've got a sum over graph of this type. And now, to each half edge, I've got an integer k1, k2, k3, k4, k5, k6, k7. So each edge, whether it comes from the internal edges or from the leaves, carries an integer k, or I should call it d, here, which is arbitrary. And so the sum I'm performing here is the sum over a stable graph, so which has this constraint here of given genus with n ordinary leaves, an arbitrary number of these dilatant leaves. But in addition, I've got to sum over all possible decoration of the half edges. So all possible assignment of a positive integer to this. And what is the weight of such a stable graph. This is the weight which is obtained just by computing this residue here. And I get it just by saying, OK, I'm doing some Taylor expansion in the capital Z. And I will just look, for example, for the edges here. Just look at it as a Taylor expansion in capital Z0, capital Z1. I get a series whose coefficients are given by some BKL ij Z0 of E to the power K Z1 of E to the power L D Z0 of E dZ1 of E. So when I will perform my sum over my residue computation, what I will see is that I will have for each edge a sum over K and L of contribution, which depend on this K and L. And so this is exactly why I had to introduce this additional parameter, just in order to select which of the coefficients on this expansion I will get a contribution from. Now the weight of gamma is just a product of contribution coming from the vertices, product of contribution coming from the edges, contribution coming from the ordinary ellipse, so let's call it Li, product over H which are dilaton-leaf of contribution of H. Now, what is this contribution? So for vertices, if I've got a vertex of this type, so I've got G, I, I've got N, valency of G incident edges, so let's call it, let's draw it in this way, and I've got some integer, D1, D2, dk, where k is the valency of my vertex. This is just given by the intersection number tau d1, tau d2, tau dk, g, k, because this is the result of the topological recursion for this simple guy. That's what we did compute in the first lecture. And there is actually a prefactor here, which is that in the computation we did set h1 is equal to 1. No, just changing h1 is just changing some homogeneous parameter, so it gives you 2 minus 2g minus k. So the contribution of a vertex is as simple as that. And so going back to your question, if you take the case where b equals 0, h equals 0, except for the first one, just have graphs which are just one vertex, and it gives you just one contribution here, which was the original formula that we had. Now what about the edges? The contribution of an edge going from a vertex of type G1, I1, to another one of type G2, I2, with K1, K2, associated to the two different parts, is simply given by, it's here, 2K1 minus 1 double factorial, 2K2 minus 1 double factorial, bk1, k2, I1, I2. So this gives me the contribution coming from the internal edges. Now let's go for the two last one. The contribution coming from an edge of this type G I K is equal to 2k minus 1 double factorial h 2k minus 1 I. So as I was saying, this just amounts to introducing this h case. So if you want to switch them off, you just have to remove these dilaton leaves. And finally, the contribution coming from these ordinary leaves. Got the G, I, K, I1, theta 1. Then this contribution is equal to a residue when z goes to 0 of 2k plus 1 double factorial dz divided by z to the power 2k plus 2. And you take a primitive of omega 0,2 of I1 theta 1. And the second one is I C prime. And this is Z prime, which goes from some reference point to Z. OK, let's do that. Yeah, it would be a D everywhere, actually. And I guess I did it here as well. D1, D2, D2, D1. And yeah, indeed, especially because I've got this K. Yeah. Yeah, I mean, the weight of one stable graph equipped. OK, so you say without before summing over this? OK, no, yeah, it's a finite sum. Yeah, because of the restriction here, which makes that the sum of the di's need to be equal to 3g minus 3 plus k. You've got an upper bound on the values that you can have here. So yeah, you don't have any such issues. So now you can play with different things. So one way to think about it is to say, actually, what I did represent here is the way of thinking about all possible deformation of the curve I started from. So if I want to look at what happened when I just change a little bit omega 0,2, it will just impact the BKL here. And so it will just impact the weight of these internal edges. Now, if I just want to change the omega 0,1, it will just impact these external edges. So I've got a very good control on that. And actually, let me just recast this sum of a stable graph in a way which might be more transparent. So the first thing yeah. Sorry? Yeah, but you don't have any, no, you don't have any factor here. It's just one for all of them. You don't have any automorphism which will act there. Because you've got mark points here, and it will fix everything. So yeah, you could, but it would be equal to 1. It's like in the case of maps, I said that in the definition I gave, I should have 1 over automorphism, but as soon as you've got one marked face, you don't have such an issue to consider. OK, so I've got this sum over stable graphs. Now, the first thing I want to point out is that omega gn of I1 theta 1 in theta n it is a polynomial in the following function. Yeah, let's do it here, since I define it here. If I call this psi d, psi di of theta 1 I1, if I define it in this way, that's a differential in Z1. So you see that you're integrating omega 02 is a one form in Z1 and one form in Z prime. But one form in Z prime, which I integrate, it gives me a function of Z, which is a differential in Z1. I integrate it against a differential in Z, so I get a differential in theta 1. If I expand my omega gn in the basis of such differentials, it gives me a polynomial. And this follows from exactly the question you asked, which is, do I have an infinite number of contribution? So it's a polynomial in the form theta, psi I d ij theta j, meaning that I can write it in this form. This is equal to a sum over d1 to d n, sum over, let me call it alpha 1 to alpha n, of some coefficient, which I call c, g I1, alpha 1 d1, alpha n dn, product from j is equal from 1 to n of psi dj alpha j ij theta j. A priori, this sum would range from 0 to infinity here. And this goes from 1 to n. But because for a given graph edge can just have a finite number of them, I will have just a finite number of these coefficients. So it gives me polynomial in this basis of differential. What I'm doing here is that just writing down this omega gn, which is a multi-differential symmetric, in a very specific basis of differentials. And the claim is that because of this formula, it gives me a polynomial in this. So it's a very rich structure and very rigid. I started from something which was depending on an infinite number of parameters. Now I recast the information into two parts. One part, which is this part, which indeed depends on an infinite number of parameters, and another part, which is just a coefficient of a polynomial, let's say. OK. Now, my point is that, yeah. Sorry? So you can write it as a function of the h here. So what you could do as well is write it as a polynomial in the h case by adding some other term. Yeah. OK. So I think I will stop here for this part. And now I will just tell you why I did all these computations. So the first thing I did was that given such a curve, arbitrary one, this theorem gives you an explicit formula of your omega gn in terms of stable graphs. And the weight of your stable graph was just coming from intersection number, so integral over mgn bar. So it's a very nice formula, which, yeah, I should have said it, was derived by Enna in this general setup, and which will prove to be very important in application to enumerative geometry. So one of the great success of this topological recursion procedure is that it magically appeared in different parames of enumerative geometry, so ranging from the enumeration of maps, which I described in the first part of this lecture, to the computation of volume of moduli space of bordered Riemann surfaces, or enumeration of Hurwitz number, and also computation of Gromov-Witten invariance. And in all these cases, it was a case-by-case proof, let's say, of the fact that the topological recursion was giving you the right answer. So a big question is, why does it appear in all these cases? There should be some kind of hidden geometrical reason. And the reason for that is that many of these examples come from cohomological field series. And the whole point of this computation is that the structure which is there will appear again in the cohomological field series setup. So what is a cohomological field theory? So you consider A, which is a finite dimension vector space. So let's write down dimension of A is equal to capital N, to stick with the notation I had before. And you want it to be equipped with a non-degenerate symmetric bilinear form. I'm not writing it. So which is a map from A, tensor A to C. So we start from this data, and a cohomological field theory, which I will write on coFT, built on A, this finite dimensional vector space, is the data of a set of cohomology classes, omega gn, for 2g minus 2 plus n strictly positive, which are cohomology classes in MGN bar. But they take value in the tensor product of n copies of the dual of A. So to be a bit simpler, it means that for 2g minus 2 plus n, strictly positive, you've got that omega gn. If you give it n vectors, it gives you a cohomology class in MGN bar. Now, it is a set of such omega gn satisfying the set of axioms which I will write down now. Okay? And these axioms will basically be some kind of gluing axioms which appear naturally when you want to build some kind of field theory. So first, what you want is that you want to put some constraint on omega 0,3. So first example of this case is when you take g equals 0, n equals 3. So it satisfies that. In this case, mgn bar has dimension 0. So actually, omega 0,3 is just a map from A tensor A to C. And what we request is that first there exists an element 1, which is a very specific element in your infinite dimension, in your vector space A, such that if you take omega 0,3 of A1 tensor A2 tensor 1, this is equal to B of A1 tensor A2 for all A1, A2 in A. So here I'm just using this this bilinear form. Sorry, I didn't give it any notation. So this bilinear form, this map from A tensor A to C, I call it B. And so what I want is that there exists some very specific element, which I will call unit, in A, such that if you take omega 0,3 and you feed it with A1, A2, and 1, you get this bilinear form. Actually, a good way to write it down would be this one. So integral over M03, which is a point. Yeah. Yeah, so that's the second axiom. Omega Gn is symmetric in the n variable. So yeah, it is symmetric. So this, for example, this I could put A1 and A2 wherever I want. So see now, what I want is that I want to have some gluing axioms. So let's first consider the following gluing map. I take an element of mg n plus 2 bar. And and I get an element of mg plus 1 n. What I have in mind here is you take an element of mg n plus 2 bar. So this is the 2 here. And I will glue these two points together. I get an element in mgn bar, actually in the boundary of an mgn bar. So I get a nodal curve just by gluing together these 2 points. So I call pi1 this map, gluing map. And what I request is that, if I take omega g plus 1 n, and I associate to this, what I want is that here I could put an arbitrary element of my vector space E. So here I will call EI I equals 1 to n, a basis of A. I could write it independently of the basis, but I think it's going to be easier if we do that. And what I will say is that here I could put, if I put an arbitrary element, EI, EJ here, I will get back what corresponds to having EJ, EI here. And this, you can write it in this form. If you take A1 tensor tensor an. And you pull back by pi 1 this class, you get a class in the cohomology of mg n plus 2 bar. And I want it to be equal to omega g n plus 2 a1 tensor an, the same arguments. But now I've got two of them in addition. I've got I1 tensor, I tensor, EI tensor EJ. I want to sum over I and j taking arbitrary value, so being any element of this basis. But what I do is that in order to get that, I multiply it by b of EI, EJ for taking into account the pairing between these two is. Yeah. Yeah, it's b minus 1 here. Yeah. It should be, yeah. It's the inverse matrix. So if you look at the matrix for the element R, B of EI, EJ, you look at the inverse matrix and you look at the element IJ. And this is the factor that you put here, okay? So what I want is that I want my cohomology class to be consistent with this kind of gluing procedure. So that's one case of gluing. Now, I can consider the other possible gluing. You remember that in the degenerations that we consider, so going the other way around from this side to this side, I could keep my surface connected, or I could disconnect it. So for example, you will have a second gluing, which is pi 2, you take G1, N1 plus 1 bar times M, G2, N2 plus 1 bar to M, G1 plus G2, N bar. And what you want is exactly the same kind of condition, that if you pull back the class associated to this part, so let's go P2, pullback of omega G1 plus G2 and A1 tensor A, it's N1 plus N2, N1 plus N2. It's equal to, yeah. Sorry? No. Here? No. I mean, I take the inverse matrix. So yeah. Okay. So our dual. Yeah. I mean, you call it prime. What? Yeah, but. Yeah, but you could write it also as B of the dual guys. So that's why. So the. No. So. I primed. Yeah, but so here I've got some I and J. Yeah. Okay. Then. No. Yeah. Okay. Yeah. So what I was going to do is to call it Bij. You're right. So this is okay. Okay. So yeah, so it's N1 plus N2. And I want it to be equal to just a product of the omegas I would have here. So omega G1 N1 plus 1 A1 tensor A N1 EI tensor the same with 2 A N1 plus 1 A n1 plus n2 tensor ej sum over I j from 1 to n, and you've got the b e I prime e j prime minus 1 and I j. So the same factor. So I'm just doing exactly the same thing in this gluing case. And I just want to have a last condition, which can also be thought of as a gluing condition, but actually it's a forgetting condition. That if you take the forgetful map from, let's call it P3, mg n plus 1 bar to mg n bar, you've got your surface genus G with a bunch of mark points, and you forget the first one. So 1, 2, 3, 4. 2, 3, 4. Then you want that your cohomology classes behave in the right way, meaning that if you take omega g n of A1 tensor AN, and you pull it back by P3, the cohomology class here, it's omega g n plus 1. And now the first one is just this very specific element 1, which I defined before. AN. So I want that my cohomology classes satisfy all these axioms. So I want symmetry, I want some nice gluing property, and I want that 1 allows me to forget one of my mark points. So one way to translate, for example, this would be to say that it's a rather tricky way to define some omega 02, which doesn't make sense from the MGN bar point of view because M02 is not defined. Yeah? Sorry? No, you mean summing over the AIs, you mean? No, yeah, I don't sum because here I've got the gluing map. Not a cutting map. So this map tells me how to take a bunch of A. Yeah. Yeah. So no, I don't sum over partitions of n plus 1 elements. I mean, otherwise I would have to sum over also n1 plus n2 and so on. Okay, so that's the definition of a cohomological field theory. And in particular, if I've got cohomology classes, I can integrate them over the fundamental class of MGN bar. And I can define what I will call correlators, which I will use the same notation as before, TK1 of A1, TKN of AN, GN, and I put a cohomological field theory here to say that it's for a given cohomological field theory, which I define in this way. And this is a notation for, you take omega Gn of A1 tensor A2 tensor etc. tensor AN. So it's a cohomology class on MGN bar. I can multiply it by a product of other cohomology classes, for example, psi classes, which are classes in H2. And I can take power of them. This still gives me a cohomology class. And in order to get a number, I integrate it. So you've got the cohomological field theory, which is the data of cohomology classes. But actually, what I will have access to and some important property in order to know these cohomology classes, it will not give you all the information about them. But in order to extract information, I can compute numbers just by integrating it against some psi classes. And this number will be produced by topological recursion. So I will just give you, after a short break, I will give you 2 examples of cohomological field theory, and just to tell you why it's important to get them. Okay. Okay, so I gave you a definition of what is called a cohomological field theory, which I think in this form has been introduced by Kontsevich and Manin. Now, one question is, why do we want to have such things? The point is that these cohomological field theories, they appear in different fields of physics and mathematics. And I will give you just some brief examples. So probably the most important one, and I think it was the motivation for the introduction of cohomological field theory, is the case of Gromov-Witten theories. So basically what you want is to say that you've got X, which is a manifold, and you want to count maps from a genus G surface with n mark points into X. So there is a good way to make sense of this counting. And so you could call NGN the number of maps of this type from sigma Gn to X. But you can have some additional constraints. If you take A being in the cohomology of your target manifold X, in some sense you can require that your n mark points, they will land on some specific locus here, which are obtained by Poincaré duality on A. So you take a cohomology class here in X, it gives you by duality homology class, and in some sense you will enumerate maps of this type where your n mark point should land in these fixed homology classes. So you just take A1, AN. Now this is what is known as Gromov-Witten invariance. And now I use the same letter to say that it is a cohomological field theory with the following thing, which is built upon A, where A is equal to your cohomology in X. So there is a nice way to write this down, and one way to think of people usually talk about quantization of this cohomology. So if you take A to be the cohomology of X, then you can build a cohomological field theory on it. And the correlators that you will build in this way, this number, they will basically count the number of maps from a genus G surface with n mark points into your target space X with some fixed constraint on the position of the mark point. So I would say it's one of the big motivations for that. So it's a counting problem. Now, a dual prime, which is not of enumerative nature, is coming from Landau-Ginzburg models. Or sometime you will see a Saito theory. It's very related to that. And the data is a little bit different. You're given a pair yx, where y is a manifold, and you've got a map from y to c. So the dimension of my manifold can be anything, so it's a complex manifold. And I ask that x has simple critical points, or as Morse critical points. So a simple example is when you consider y to be of dimension 1 complex, so it's a surface. This defines for you a cover of C. It's basically the example we started with, which is the data of a spectral curve. So you can think of a spectral curve as a Landau-Ginzburg model where your space Y has dimension 1. Okay? Now, if you've got something like that, there is a natural algebra of vector space which has some algebra structure which appears, which is the Jacobi ring of X. And how is it obtained? We'll just give you an example. If Y was C to the power n, with coordinates Z1 to Zn, then what I call the Jacobi ring of X is what? You take the ring of polynomial in n variable, but you mod out by the relation given to you by the partial derivative of X. So for example, if it has, let's look at a simple example. N equals 1, one-dimensional. And I take x of z is equal to z squared. Z4. Then what you get is that you mod out by z. Let's take z squared. Then dx over dz is equal to z. So you will look at the polynomial in z modulo z. So you just have the parity which amounts to it. And now there exists a cohomological field theory which you can build on this Jacobi ring, which is interested actually in the deformation of complex structure of your manifold Y. Yeah. Where here it's going to be a residue pairing. So you take two polynomial, take the residue of their product time volume form here. You've got to be careful, and it gives you a number. So yeah, this gives you the vector space, which is finite dimensional. Actually, you can see that the dimension is equal to the number of branch points of this map, X, which should remind you of what happened in the spectral curve case. And the pairing is given by some residue pairing. So these are the two main examples I will talk about of cohomological field theories. There exist other ones, but these are the ones I will be interested in. So on the left-hand side, on the Gromov-Witten side, I really have an enumerative interpretation of these numbers. And basically, the aim of many work on topological recursion were to compute this Gromov-Witten invariant and say, oh, but they are given by a correlator of a cohomological field theory. Now, do I have a way to compute this correlator of a cohomological field theory? And the answer will be that yes, you can. And you can always do that using the topological recursion under some assumptions. Yeah. So the main assumption we will have to do which is very closely related to the assumption I did on the spectral curve saying that I had just simple branch points, or saying that y here was starting with z, with zeta, is the semi-simplicity assumption. So we say that a cohomological field theory is semi-simple if actually A is semi-simple, which means what? It means that forgot to tell you about one thing before, sorry. I will do it here. So you can wonder why I call a vector space A. I could have called it V. So the reason for that is that it has an algebra structure whenever you've got a cohomological field theory. So when you've got a cohomological field theory, you've got this omega 03, which takes 3 elements of A and gives you a number. Now you could say, OK, I could use that in order to define a product on my vector space. Yeah, 0, 3. I can use it in order to define a product in the following way. You've got A1, A2, A3. We will define a product A1 times A2 on A, on your vector space, by defining that the pairing of your product A1 to A2 the pairing of A1 times A2 with A3 is defined to be just the omega 03. Now, if you take the first axiom I gave to you, was that there was some identity element in A. So let's take A1 is equal to 1, which I did. And I was saying that it should be equal to B of A2, A3. So this is consistent with 1 being the identity for the product I defined here. And actually, this product gives this vector space equipped with the product a structure of Frobenius algebra. So you've got A, you've got the product, and you've got B, which in particular means that you have a commutative product because of the symmetry, but in addition, you've got this property, A1, A2, A3. So you can use the full symmetry of your omega 03 to take, for example, A1 on the other side. Meaning that you've got a compatibility condition between the pairing and the product you defined. So if I've got a cohomological field theory built on A, it means that A is no longer just a vector space, but you can think of it as some Frobenius algebra. So you can define a product on it. Now, I say that a cohomological field theory is semi-simple if A equipped with this product, which gives it a structure of algebra, is semi-simple. It means that there exists a basis of A which diagonalizes the product. So let's write epsilon I from 1 to n, this basis. It means that I have a basis where epsilon 1 epsilon j is equal to delta ij epsilon I. And actually, in order to describe this algebra, or more than that, if I want to describe this Frobenius algebra, so now I need to know how B is defined. So I describe the product here. Just need to define the norm of this element of the basis. And this will be given by delta ij, and I will denote it by 1 over delta I. So delta I is the inverse of the norm of this element with respect to this linear form. So the semi-simplicity assumption is that there exists a basis which diagonalizes the product. So which one? Yeah, exactly, yeah. So another way to come to cohomological field theory is that they are not only in correspondence with Frobenius algebra, but with Frobenius manifold. And so you will have associativity, but you will have more than that. You will have what is known as WDVV equation. So there is a correspondence between this cohomological field theory and the Frobenius manifold structure, which was defined by Dubrovin. And it did, yeah. You can think of this axiom as giving you back actually a generalization of this associativity of the product. Now, the Frobenius algebra, actually, you can see it just by looking at a very particular part of your cohomological field theory. And yeah. And this is what I will discuss right now, but very shortly. Okay, I've got some time. Yep. Yep. So remember omega gn of A1 tensor AN is a cohomology class of arbitrary degree in MGN bar. Now, I could look at just a restriction of this cohomology class to the degree 0 part. So in particular, if you, I don't have this correlator formula, but it means that if you look at the degree 0, what I call the correlator, or the degree 0 part coming from the correlator, will be object of this type, MGN bar, product from I equals 1 to n, psi I to the power ki, omega g n 0 of A1 AN. But these are just degree 0 cohomology class, so actually this just gives me a number which I could put outside here. So what I will end up with will be numbers times some integral of product of psi classes, and here you recognize the intersection number I computed in the very special case of the curve X, where all the H and the B were not there. So actually, this restriction is a very important object, and it gives rise to the data of the omega 0 gn is what you know is the same as the data of a two-dimensional topological quantum field theory. TQFT in short. So if you just look at the degree 0 part, and if you look at the relation I had before, if you just look at the degree 0 part, it will give you some new axioms, which are the axioms for a topological quantum field theory. And in particular, it is known that this topological field quantum, this TQFT, they are in one-to-one correspondence with the data of Frobenius algebras. Now, if you know a little bit about TQFTs, you know that there is something which is called the fail in the formula, which allows you to compute correlators of these TQFTs, which are basically these integrals which I do right here. And the idea behind is very simple in this semi-simple case. The result is the following one. If you just look at the degree 0 part, yeah, how do I put that? The omega, I called it 0, yeah. Omega 0 Gn. So if A is semi-simple, then there exists such a basis. And now I can just write down this omega Gn in this basis. Epsilon I1 tensor epsilon In. If you would put G equals 0 here, actually you see that the first step is that if you take G equals 0 n equals 3, it is just a product in your algebra. So it is diagonal, so it's vanishing unless all your 3 indices are equal. And you know the weight coming from this relation. Now, if you're in the higher genus and higher n case, the big difference between the topological field theory and your cohomological field theory is that this theory is topological, meaning that if you've got a surface with a bunch of insertion, and whatever you've got here, the correlator associated to this surface should be the same as the one associated to any surface you would get by degenerating it. So just taking cycle and pinching it. The value of your correlator will not change. And in particular, you could look for a pair of fund decomposition of this surface. So let's take an example, this one. So the correlators in your TQFT associated to that has to be equal with the same obtained by just taking a pair of fund decomposition, with this being one boundary of your pair of bonds. And then just shrinking that. So what you end up with is just a bunch of spheres with three Mach points. Which are glued together. Now, in addition, the gluing axiom in this TQFT case tells you can write it down. You know, you've got just to sum over all possible insertion of element of your algebra here. And the weight associated to each three-pointed sphere is just the omega 0,3, the degree 0 part. So the result of this evaluation, so this correlator, is just the product of the omega 0,3 there, so just three products, where here you put an arbitrary index epsilon I1, epsilon I2, and I3, epsilon I4. So here I have some epsilon I, and keep on doing that. You sum over all of them, and the weight of each sphere is just the omega 0,3, so just the product in your algebra. But this product is diagonal. So this forces to have that all the i's here, which I have, should be the same. So actually, I don't have any sum here anymore for this gluing property. I've got the same epsilon I everywhere. And what I end up with is just a contribution which is just coming from knowing just these products. So this gives you 1, this gives you 1. But then if you've got a genus guy, you will have contribution coming from the norm of your epsilons. And you can write down the result. It's just delta I1 to the power g minus 1. And this is non-vanishing only if all the indices are the same. So if your theory is semi-simple, the correlators can be computed explicitly. This is just this number here times the integral of your psi classes over mgn bar, which we did compute before. And so this, we can think of it as being equivalent to saying that this comes from topological recursion for omega 0, 1 I of omega zeta I being just, let me check the delta function. Yeah. Delta I to the power minus 1/2 zeta square d zeta, and the usual omega 0, 2 zeta 1 I1 ij zeta 2, which is diagonal, d zeta 1 d zeta 2. Up to some rescaling of your zetas. So now I'm just trying to mimic what I did for the topological recursion. Start from the simplest case, this degree 0 part. And in the recursion case, this was this simple plus curve. And then I got a formula which was telling me how I can deform that. Now, the wonderful thing is that there is an equivalent in the case of cohomological field theory. And this would be a reconstruction procedure of omega gn. Which is due to an idea of given tal, and which was proved by some classification theorem of Telemann. So what's the idea behind that? Yeah. From I should say it, from omega 0 Tn. So the question is the following one. In the preceding case, was telling you if I start from that, I can reconstruct the result of the topological recursion by introducing this infinite number of parameters by using this sum of graphs. Here I will have something very similar, which is if I know the omega gn 0 and I know the equivalent of this deformation here, I can reconstruct omega gn. And it will be a sum over stable graph as well. It will be the same. OK, so what's the idea for that? The idea is that there is some group acting on your cohomological field theory. Which is the action of some infinite dimensional group. You can think of it as some infinite dimensional symplectomorphism. I will just give you how this works. So you've got two types of action, two types of group elements. You first have some translations. So what is a translation? You consider some T of U, which is a series in U which starts with U2. So let me write it as sum over M greater or equal to 0, Tm U to the power M. So U is a formal variable, and each of the Tm's are elements in A. So in our original vector space or Frobenius algebra. Now there is some operator associated to it, which I will call T hat, which was obtained by some quantization procedure found by Giventhal, which acts on your cohomology classes. So if you've got a cohomological field theory built on A, there is some action of an operator built from T, which is such that if you take the result of this action and you look at its evaluation on A1 tensor AN, it is equal to what? And here you will recognize something. You take omega G n plus n. So same G, but now you don't have only n variable, but you've got n plus m variable. The n first one, you don't touch them. The m following ones, I shouldn't have called it m. Sorry, let me call it K. Will be Tm1 tensor Tmk. So you introduce k new elements of A, which just come from this series expansion of your T of U. So you sum over any number of insertions, sum over k from 0 to infinity, 1 over k factorial, just for the permutation of these elements, and sum over m1 to mk, ranging from 2 to infinity. Now, this is a cohomology class in n plus k, in mg n plus k bar. So you've got to pull it back by some forgetful map. Push it forward by some forgetful map into a cohomology class in mgn bar. And before doing that, you will multiply it by product from j equals n plus 1 to n plus k of psi j to the power the index which is here. So if I've got psi corresponding to this one, so psi n plus 1 at the n plus 1 insertion, I've got the power m1. So it's m j minus n. And you push forward this big cohomology class into a cohomology class in omega gn by just this forgetful map, Pm, which goes from mg n plus m. So I should call it pk, sorry. Pk, which just forget about the k last point, mgn. Wow. So basically, you do something you've seen already before. You just insert an arbitrary number of new elements which are coupled to some higher power of psi classes. And the weight is given by the elements that you translate from. This can be really thought of as switching on this H here. So this T of U, you can think of it as shifting omega 0, 1 by a function of zeta, and the Tm's are just the coefficient of this expansion. Now you've got just a second class of group element I will need. Sure. Because I want J to be, so J tells me at which place I insert my psi class, and it's the J plus nth point. If I would have put my A's on the other side, it would have been simpler. So the second class of group element is what is called some R matrix action. And this is a little bit more tricky, but the idea is that we will have something which corresponds to the deformation of this second part. So in this part, we had a translation which just knows about one index I. Here we will have something which will depend on two indices I1 and I2. So it will actually, instead of being a series whose coefficient are element of A, it will be a series whose element are endomorphism of A. So I start from R view, which is a series in U. Whose coefficient are endomorphism of A. And what I ask is that R0 is equal to the identity. And so, yeah. So basically, if you write it as R view is equal to sum over k, rk, u to the power k, these belong to endomorphism of A. So you can think of it as a bivector. And what I'm asking for is that the coefficient in front of, the constant coefficient is equal to the identity in A, okay? Now, there is another constraint, which is a kind of simplicity, which is equivalent to saying that I've got some symplectic elements here, which is that if you take the dual with respect to the pairing B in A, is there a minus u, and change the sign of u, multiply by R of u, then it gives you a priori a series in U whose coefficient are endomorphism of A, but actually it just gives you the identity. So that's a constraint I want. So it acts on the space of, on some loop space, which is the space, a space of series in U, whose coefficient are element of your vector space A. And it acts by translation. Yeah? So if you would act, so it will just be a shift of the coefficient. So if you think of it, just think of it in this way. If I think of this as element of my algebra, basically what I'm doing there is that I will just take this element and shift it by tk. So that's why this is called the translation. So it's acting in some infinite dimensional space, a loop space associated to A, and it's acting in a very simple way in this case, just translation. Yeah. So that's what I will say after, yeah. So the Frobenius algebra, the vector space is the same. So the Frobenius algebra actually will be the same because you cannot change anything in omega 0, 3. So you cannot put any cohomology, any psi classes here because you already have something which is of dimension 0. But you're changing completely your cohomological field theory. So the degree 0, if you want, is not changed, but the cohomological field theory will completely be changed. And the idea will be that with these two type of element acting, you can always find in the orbit of a given cohomological field theory a point which is a cohomological field theory, which is a very simple one. If I'm not wrong, it should be the same. Yeah. And one of the reasons for that here, you can see directly here. So I start with U2 here, meaning that here I've got to introduce some psi classes. So if you look at the degree 0, you can only have k equals 0 here. So it increases the degree. So I've got more constraint on my R matrix action. I start from some series in U whose coefficient are endomorphism of A, and I've got this symplectic condition, and the fact that the first coefficient is equal to the identity. And if I start from that, I can define an operator in the same way, acting on omega some cohomology classes. And how is it defined? So it's a sum over gamma, which are stable graphs. Of genus G. So the genus of your graph is, once again, it's the sum of the geni of the different vertices plus the number of loops with n ordinary leaves. So you remember that I had these two kinds of leaves, one which was this cross and the other one, and I don't have any leaf with a cross. I don't have any of them. I just have the other type of leaves, and I've got n of them. And then I just give, once again, a weight of contribution. So the formula will be very similar to what we had before. It will be a product over, let's put it here. Product over V being vertices of a contribution of V, product over edges. Times the product over, should be E here, product over leaves of contribution from the leaves. This will actually give you a cohomology class in some big space, so you will have to put some automorphism of gamma here. And it will give you a cohomology class not in MGN bar, but in some other space. And I will once again have to push it forward to a class in MGN bar. In order to get this class here. And so what is this push forward? It's the following one. So yeah, let's make a drawing here. You've got a stable graph. We've got vertices which are linked by edges with leaves. G1, G2, G3. OK, so you've got this type of graph. And now what I will think about when I look at this graph, I will just think about the kind of nodal curve I had before. So what I will associate to a vertex, I will associate a class in M G1, 3 in this case. So a class in MG of V, valency of V, and the same for each of them. And so the result of that will be just a tensor product of all these cohomology classes. So it will be an element of the product over all vertices in V of gamma. And for each vertex, I've got a cohomology class in MG of V, valency of V. And so there is a natural map from that to MGN bar, just by saying that such a curve, you can think of it as a very particular type of nodal curve in the boundary of MGN bar. So you look at an element of your MGN bar, and you look at nodal curve, once again, which are obtained by pinching cycle, let's say. And you will look at all type of surfaces which are obtained by pinching cycles, such that the pinch cycle can be replaced by these edges, and the stable components, I mean, what is between these edges are genus G of V, valency of V type surfaces. So there is a natural map of this type, and what you do is that the contribution I will give to you, you just push it forward by this map. Now, what are these different contributions? It's going to be obtained exactly in the same way as before. So for, let's start with a vertex. The contribution of a vertex of this type, where did I put it here? Yeah. So you take G, and it's n-valent. It is just equal to the class omega Gn. G of V. Yeah, so 1 to k, omega gk. So the one on which I want to act. Contribution of an edge, E, is what? So, it's equal to some function which I will call B twiddle psi prime, where psi is a cohomology class which I will associate to an half edge. So to each of the half edges, you will associate some cohomology classes psi1, psi2, psi3, which will be used in order to define a product with the omega g, which I have here. So here I've got some psi and psi prime associated to the part of the MGN bar, a different product in the MGN bar corresponding to the different vertices. And this is given by such a function where B twiddle can be computed explicitly. It's a series in U1 and U2, which is obtained by taking B dagger minus R of U1 tensor R of U2 B dagger divided by U1 plus U2. Well, now let me explain my notation. B dagger is a bivector. And basically, this is what I use for gluing my cohomological classes in the preceding case. So you can write it in a basis. I will not have time to do that right now. But so the weight is given by such a series in U1 and U2. And the fact that it is a series in U1 and U2 follows from the condition I did put on the R matrix I taken, because here you could have a pole when U1 goes to minus U2, but it will be canceled out by the evaluation here. So here I gave you two parts of my contribution, and the last one is simply that if you've got a contribution coming from a leaf, it will be just R of psi. So all in all, I get that the action of this R matrix on cohomology classes give me a new cohomology classes, which are some of a stable graph, whose weight is given by series computed in terms of only one thing, just this R matrix here, which I gave to you. Yeah. Now, so here it's like the first step I did before having the labeling of your half edges. I computed some residue, where the weight of my edges was given by some omega 0,2s. Here it's the same. This actually will correspond to a Laplace transform of omega 0,2. Now you would have a sum over labeled half edges by making an expansion in U1 and U2. If you do that, you will have powers of psi's here. And so you can associate the degree to half edges, which correspond to the power of the psi class that you put. So indeed, when you want to compute after that the integral over mgn bar of the result of the action of this R matrix, you can write it explicitly as a sum of a stable graph where you've got this degree decoration. And now the weight of an edge which is decorated from K to L will be obtained just by looking at the U1 to the power K, U2 to the power L coefficient of this series. Okay? Is it clear or not? No? So here I get a series in U1, U2, but what I want to do is to put my psi and psi prime here. So if I write B twiddle of psi 1, psi 2, this will give me something like sum over KL, B twiddle KL, psi 1 to the power K, psi 2 to the power L. So I will replace an edge with psi and psi prime by a sum over K and L of edges with KL, which means that I've got a psi to the power K, psi prime to the power L. But the weight of this edge now will be B twiddle KL. And that's exactly the result of the computation of residue I did in the other side before. So now, so psi and psi prime. So if I look at this vertex. What I associate to it is some omega G1, 3, so which is a cohomology class in this. Now, on this space, I've got some natural cohomology class, psi 1, psi 2, and psi 3, which are degree 2 cohomology class in this M G1, 3. Well, so I'm just considering them as cohomology classes. And so the result of this sum is that I will have a cohomology class for this one, where you've got some psi factors, cohomology class from this one, where you've got some psi factor, but which correspond to the second factor in this product, cohomology class for this factor, which correspond to the third product in this the third factor in this product. Now I will kind of put them together by pushing forward by this map. But a priori, the psi classes are psi class associated to an half edge incident to a vertex corresponding to one of these factors is a natural psi class here. So it's a cohomology class. Yep. Oh. So let me state the result now. It's going to be pretty fast. And this is a result which was obtained by a classification by Telemann, which states that for any semi-simple cohomological field theory, there exists R and T such that omega Gn, so the cohomology classes you want to compute in this cohomological field theory, how do you get it? Just take the degree 0 part. You take the degree 0 part, and you act on it by translation and R matrix action for the specific R and T. Now, even more than that, in many cases, these R and T are uniquely determined, and there is a very explicit procedure for computing them. Now, what does it mean? It means that if you want to compute Gromov-Fulton invariance, what should I do? So there is an associated cohomological field theory. If I'm lucky, and this happens in many cases, it is semi-simple. So now, what do I need to do? I don't have to compute all these integral of cohomology classes. What I need to compute actually is only the degree 0 part, but I did it for you earlier. And I need to compute this T and this R, because after that I know it acts. This can be done under some constraint, but there is some way to do it. And now the beauty of that is that the sum over graphs that you have here is exactly the same as I had before in the topological recursion case. And so it means that actually the integral of these cohomology classes along MG and bar, when you take a product of psi classes in front, can be written in this form, sum over a stable graph. It will map exactly to the sum over a stable graph you get for the topological recursion. The only thing you've got to do is to define a recursion such that the weight of the two sum over graphs coincide. And this is obtained just by fine-tuning your B's here and your H here in such a way that they map to your R and T. And actually, that's pretty easy, up to some double factorial. The B which is there is just the B twiddle which is here. And the H which is there is computed very explicitly in terms, actually, of just the coefficient of your R matrix. So there is a very good map between the two of them. So in the preceding part of the lecture, I told you how to deform curve. Now I'm telling you that when you want to deform cohomological field theory, it's exactly the same thing. And so this means that topological recursion will give you a formula for correlators of such cohomological field theory, and in particular, Gromov-Fulton invariance. And if you look at the cohomological field theory associated to a Landau-Ginzburg model, which I showed you earlier, where my manifold was of dimension 1, it was giving you actually exactly the same formula that I've got here for the omega 02. So I don't have time to talk about that, but the nice thing is that in some cases, you've got some very explicit formula for R and T. But in general, you know that you will always have this procedure which maps to the topological recursion. So if you think cohomological field theory, correlators in cohomological field theory, you should think that if you've got this semi-simplicity, the only job you've got to do is to find this R and T. OK, so I think I will stop here.